Alright guys, welcome to this week's video. It's based on integration, and this is what we're going to be looking at during this week and for a fair bit of this term. I'll start with our learning goal, and it's to investigate the concept of integration and to enable students to further use calculus to solve mathematical problems relating to rates of change. Now, we've already looked at problems involving rates of change. That's basically what our derivative problems use. So we have found rate of change of a displacement. The rate at which our displacement changes gives us our velocity. The rate at which our velocity changes gives us our acceleration. So we've been doing these problems already. Integration, as you'll see now, is like the reverse process of differentiation. So it allows us to find the function if we are given the gradient function, or if we're given the rate of change of a function, we can find out what that function is. So in the example we just talked about, if we are given the acceleration function to represent the acceleration of an item, we can apply integration to work out what a function for the velocity would look like. And if we're given the velocity function, we can use integration to find out what the displacement of an object, the function, would look like. So integration, the capital F is used over here to symbolize what the integral is. I tend to use this symbol here, the integral symbol, rather than the uppercase and lowercase. I think this gets a bit too confusing. So we see here the integral of a function is given as a capital F, and the integral of the derivative gives us the original function. Now, since the derivative of a constant is 0, when we're working backwards applying the integration, we need to add a plus c term to represent that constant term in our function. So if we had the if we were finding the derivative of x squared plus 3, that would just give us 2x. We drop the 3. When we're working backwards, we've got to take that into account, that there may be a constant term. So, as I just mentioned before, if we have a function x squared, then the derivative of that is 2x. Now, if we were given the function, if we had a rate of change function, or the derivative of the function was x cubed, if we were using the reverse process of differentiation or integration, what could the initial function be? So I just give you a couple of seconds. You might want to pause now to have a go at working out that question. So when we work backwards for integration, if we have a function or a term a x to the power of n, then the integral of that, or the original function, if you like, is going to be ax to the power of n plus 1. We must make sure we add the 1, because when we do our differentiation, we subtract 1 from the index, and we also need to divide that by that term n plus 1. And we make sure we add that plus c. And now this is only applicable for n when n is not equal to negative 1. We'll look at the factor of n equals negative 1, in which case we have a function like this. We've got x to the power of n on the bottom, and we can look at that later. It should just be a over x, sorry there. So this is the general form. Write that down. We're going to use that over the course of this term. By the end of the term you'll be fairly familiar with it. Hopefully by the end of this week you'll be fairly familiar with applying integration in simple terms like this. So back to the initial question we posed. If we have a rate of change function x cubed, and we're going to use the reverse process of differentiation, what would the original function look like? So in this case, we've got our rule up here, ax to the power of n. If we just recognize that there's a 1 in front of this x cubed term, can assign the value a equals 1 and our index is 3. So by using integration, applying this rule here, we're left with a, which is 1, times x to the power of 3 plus 1 divided by 3 plus 1. So we get a function, our original function would be x squared, x to the power of 4 divided by 4. Now obviously there should be a plus c there as well. We can always check our answer with the differentiation by doing the reverse process. So by actually applying that, finding the derivative of that function, we should end up with x cubed. So just like that. And like I said, use your differentiation skills to verify your answer. Now just when we come to the exam time, you're not putting that C in, it's going to lose half a mark. So B question goes down to a B minus. It's a silly mistake to make. It's a common one, but just get into the habit of putting the plus C all the time, so it becomes second nature. And also, you should know by now in grade 12 that you should be verifying your answers. So whether you're doing it by applying differentiation here, or using your graphical calculators to verify it, make sure you do some type of verification. So a couple of rules that we're going to look at. We've already looked at this one here. This is the general form of the integration. Also, if we find the integral of two functions, that is the same as the integral of the first function plus or minus the integral of the second function. We'll look at this when we're looking at areas between curves towards the end part of this term. I think we get to that. And also if we've got a constant multiplying a function, if we find the integral of the constant multiplying a function, we can take that constant out the front of the integral and apply the integration just on that function. So if we're looking at an example now, we want to find the integral of x, 3x squared minus 10x plus 4. You might want to have a go now at doing this yourself. I've got a work solution coming up, but maybe just pause this here, have a go at working through that problem yourself using the rules we've just discussed. Okay, so we want to find the integral. So the integral of this function, so for this first term 3x squared, 3 stays the same. We add 1 to our index and we divide that by 2 plus 1. So the index plus 1 again. Likewise for this one, we keep the sign the same, nothing changes on the sign. Add 1 to the index, divided by the index plus 1, and so on. We've got a 4, that's really like saying x to the power of 0. So x, anything to the power of 0 is 1. So we add 1 to that, and we get 4x. And don't forget the c, obviously. So if we simplify that down, we get 3x cubed over 3 minus 10x squared over 2 plus 4 times x to the power of 1 divided by 1 plus c, which simplifies further to x cubed minus 5x squared plus 4x plus 3. Now, if we take that answer there, find the derivative of it, we should come back to our original function that we started with. Second example, again, encourage you to have a go at this yourself, work through it. We've got another full solution coming up shortly as well. So press pause here if you'd like to have a go at doing it yourself. So again, we'll find the integral of this function. The constant out the front stays the same. We increase the index by 1 and divide it by the index plus 1. So for this one, 5x to the power of 2 plus 1 divided by 2 plus 1, and so on, and obviously don't forget your constant value. So hopefully when you had to go at it, attempt it yourself, you got x to the power of 4 divided by 2 minus 5x cubed divided by 3 plus 4x squared plus c. Now, we don't have too many tricky rules to remember with the integration. far as we take it really is this using the chain rule. It's based on the derivative change rule. It's just done in reverse. So if we are given a function in this format, we've got ax plus b to the power of n. This is the rule that we can use to solve the integration of that function. Now it's worth remembering, you'll need to know it for your exam. It's fairly simple as well. Again, we add 1 to the index, keep the brackets, what's in the brackets the same in the numerator, add 1 to the index, and then we divide it by a, so that constant in front of the x, multiplied by n plus 1. Again, don't forget your plus c, and also it only applies for n is not equal to -1. So write that down in your books as well. We'll refer to that fairly regularly this term as well. So with that in mind, we've got the function here. We're going to look at an example. Find y if the derivative of y over dx equals 3x minus 5 squared. So y equals the integral of dy dx, which equals the integral of 3x minus 5 squared. Again, using this formula up here, identify our a value, our b value, and our n value. So in this case, a equals 3, b equals -5, and n equals 2. And then just apply the right side of that formula. So we have 3x minus 5. What's in the brackets doesn't change. We add 1 to the index. And there's a mistake here. Just correct that. We've got 2 plus 1. And I should have that a value out the front. So that should be 3, 2 plus 1 plus the c. Again, made a mistake on this one. That should have been 3. 2 plus 1. And that should be 9. So our answer is 3x minus 5 to the power of 3 divided by 9. And of course we must add that constant value on. And we can verify this using the chain rule of derivatives. So let u equals 3x minus 5. So if we find the derivative of this, u equals 3x minus 5. So y equals u cubed over 9. And you should be able to solve that and verify that you come out with that original answer. So that is the basic process of integration. I apologise for having those errors in those work solutions. When we come to class, we're going to work through some of the simpler ones, and then we're going to model that. Look at the example of where we're given the acceleration, how we can determine what the velocity is and what the displacement might be, those type of problems. So hopefully this video has made a little bit of sense, and we'll follow that up in the lessons during this week.